Welcome to the viewers. I am Tonusha Mojumdar. Today discuss very interesting result in group theory of abstract algebra. And here is the diagram you already noticed. You say G is a group, and if we consider this group, there are different types of elements, and especially we here write in this diagram A inverse equals to A and B inverse equals to B. That can say the element of the group has its own inverse, and we can prove our interesting result. Let's watch this video. And the viewer who are watching this video first time, they subscribe the channel and press the bell icon to get all the notification and latest update of my video. Now let's come to the point. Now here we are taking G be a group, and if AB belongs to G, it can be easily said that A inverse and B inverse both belonging to G. And now come to the point, if every element of a group G and is its own inverse, then this group must be abelian. This is the structure. We can say this result, if every element of the group has its own inverse, then we can say it is an abelian group. Now let's come to the part of the solution. And now let AB belongs to G. We have considered already AB belongs to G. Then their composition sign, that is group structure, A composition B belongs to G. If we say and consider here G is the composition, composition is the operational sign in G. And then the given condition A inverse equals to A and B inverse equals to B. Then we can say that A composition B whole inverse, that will be equals to, by this given condition using, we are getting A composition B. But now we are using the interesting property, but A O B inverse, that will be clearly B inverse composition A inverse. A composition B inverse equals to B composition B inverse composition A inverse. This is an interesting property, and we can prove this result in the basic theory of group structure. And now we are using here on the left hand side A composition B whole inverse, that will be clearly AOB by the given condition, and B inverse equals to B and A inverse equals to A. So this implies A composition B is equal to B composition A for all AB in G, and this type of all elements satisfying this criteria, and it is clear that it is the criteria of an abelian group. A group is considered to be an abelian if we can prove any two element and they satisfy the commutative property. So here AOB is equal to BOA, that is A composition B equals to B composition A, compositional sign. So it is clear it is simply followers of the commutative property in G. So we can conclude that G is an abelian group here. So we prove our desired result. Now let's discuss this new interesting topics of subgroup. That's the basic structure. And here in the diagram, H is a group, the G is a group, and H is a subset of G. So at first we are going to define what the subgroup is. Actually, G certainly have some structure, that is a group structure, basic group structure. Then an A non-empty subset H of a group G is said to be a subgroup of G if under the composition rule in G, which composition is defined in G, H itself forms of a group, and with respect to this composition. So this is a clear-cut structure of a subgroup. Now in this next video I will discuss few things of the subgroups and introducing here these topics as a simple theory. We end our discussion. If you like this video, like it, share it, and don't forget to subscribe the channel. Thanks for watching.